Aloha and welcome to this screencast where I'm going to first talk in general, just for a little bit, about persistency mechanisms. And then I'm going to give you a walkthrough of some code that uses a particular database system called Berkeley DB. That's the system I'm going to want you to use in the remainder of this class for our project. And I'll explain why during the screencast. Okay, so the first thing, I want to go through some of the different issues that are involved in database systems. And the primary thing is probably the data model that the database system implements. And there's a few general types of data models. Probably the oldest one is called the hierarchical data model, where you think of your data as being organized into nodes and subnodes. Cousins have the same structure, so you can see we have, a subject area called physics, and underneath it there's these three authors. You find data and insert data by traversing this hierarchical structure. And you can see that this model works really well when the kind of data that you're thinking about is XML, because XML has exactly this kind of structure. So there are some XML databases out there that you can look at, and they generally implement this hierarchical data model. One of the problems with this particular approach is that when you want to find things, you actually have to traverse the hierarchy to look for them, and that can be limiting in certain circumstances. By far the most well-known, the best studied, the most implemented, and the most used data model is called the relational data model. And I'm assuming that you've all had a course in databases where you've looked at the relational data model for at least a semester, because there's a lot to it. I'm definitely not going to try to overview all the capabilities here. Just briefly, as I'm hoping all of you are already quite aware of, the relational data model consists of sets of tables. You have a limited set of columns, but an unlimited number of rows. And you use things like primary and secondary keys to access. You also have a very powerful data access language, as well as abilities to preserve certain the so-called ACID constraints. And that enables people to build highly reliable database systems that are, maintain data integrity and are resistant to failure and have all sorts of desirable properties. Okay, so there's a reason why the relational data model is so popular. It's a really, really good one. Then there's an object data model, and the idea here is it's somewhat similar to the hierarchical model, except instead of thinking of your objects or your nodes as being essentially like XML elements, you can think of your objects as actually having state and behavior. So there's and there's not this constraint that cousins have the same structure. And so the nice thing about this is that this particular data model maps really, really well to the kinds of data structures that you have in object-oriented programming languages. Finally, I want to just mention briefly it's really kind of almost like a political movement in the database community called NoSQL. And it's a catch-all term for recent databases that have come up that are not relational in nature, but provide certain kinds of scalability, ease of use, performance advantages over certain kinds of SQL systems or relational systems in certain contexts. There's this system called CouchDB. Google's Bigtable are two examples of large databases that buck the trend of using a relational database data model. So you should be aware of that if you come across that in your readings or on the web someplace. Now, one of the important things to be aware of, and one big reason why people have problems with relational databases is that there is this concept known as the impedance mismatch, which is that programming languages, in a program, you want to generally manipulate objects, but a relational database doesn't manipulate objects, it manipulates rows in a table. Okay, and so this creates a number of design problems in terms of how you do this mapping back and forth between the objects that you want to manipulate in your programming language and the tables and rows that you want to be storing out on your database. And there's a variety of approaches, to doing it. There are a number of systems. Hibernate is a good example in the Java world, where you define a way to do this mapping back and forth, and then the Hibernate infrastructure will take care of performing the mapping kind of semi-automatically for you. Another way to do it is to just abandon the relational database backend and use an object database. Another concept that you'll need to be aware of when thinking about persistency is whether you're going for a client server or an embedded form of database. So a client-server database system is one in which the database management system runs in its own process, and then any number of clients make connections to the database and perform queries using select or some other mechanism in order to get the data in and out of the system. Okay, so that's got the advantage in that you can have multiple clients potentially written in different programming languages and running in different places, all connecting to the database system. The disadvantage is that that adds a fair degree of administrative and programming overhead. Okay. So another approach is to use an embedded database where you basically have instead of allowing many clients to connect to a server, you combine the client-server aspects together. Okay, and in this case, the database actually runs kind of essentially within the client. It makes it much more simple to set up and administer, but the cost is that only one client can be accessing the database at a time. Now that cost can be overcome when you start to think of combining an embedded database with a RESTful architecture, okay? So that you could actually have your client, from this embedded sense, communicating with other systems over the net using RESTful APIs, and then get that effect of allowing multiple, communication pathways. And in fact, that's a precursor of what we're going to be doing in this course. Okay, so client server, we've got these different data models. How do you choose which database to use? That goes way beyond the scope of this lecture or even this course. You really want to take a whole course on database management systems to really understand the issues that are involved. So I would recommend taking a class like ICS 321. In our department, Professor Lipiao Lim is a database expert, and if you're having questions about the choice of a database system, I highly recommend you go talk to him about it, because he's really an expert. But for right now, and in this class, I'm going to make the choice for you. And I've decided to choose a system called Berkeley DB. One of the reasons is because I assume that you've taken ICS 321 and have been exposed to the relational database system model, maybe used MySQL or Derby and so forth, and I thought it'd be kind of cool to expose you to a different kind of persistency mechanism. The second reason is that this is a really easy persistency mechanism to use, and in addition to its simplicity, comes with a lot of advantages. It's very high performance, it's transactional, it's cross-platform, it's open source. And so I think that we'll be able to make a lot of progress relatively quickly in the course project with a minimum amount of burden from the database side. The constraints are that this is an embedded system, but we're going to overcome that particular disadvantage in other ways, and we don't get to use the full power of a data access language like SQL, but we'll overcome that in other ways as well. So hopefully I think this will work out well. If nothing else, I think you'll have some fun using a different kind of database system than you're probably used to. Okay, so let's get out of PowerPoint and start looking at the system. The first thing that you'll want to do is download the example system. So you have to go to ICS Software Engineering Examples and click on the Downloads link. And you'll see down here, you'll see Berkeley DB, Contact DB, which is the system that we're going to use. So if you double click on that and you expand it, you'll get a directory somewhat like the following. And the first thing you want to do is type ant, okay, which is going to download some software, in particular download and install the Berkeley DB system to the lib directory. So if we go into lib, okay, and you'll see there's this Berkeley DB package, and inside there you'll see there's a single jar file called Berkeley DB-java.jar. That contains the entire database. We put that in our build path, or we include it in any jar files we create, and we've got an entire system with an embedded database in our application. So let me kind of get out of here. The other thing that you usually want to do, first thing when you download one of our example systems, is run this verify task, which is going to run checkstyle, run PMD, run find bugs, and run JUnit. And if everything passes, then you can feel confident that the system's correctly installed and configured in your system. So we ran verify, that's all good. I'm going to run another thing called the jar target, which will build a single jar file that will serve as a way of kind of demoing what this system does. Basically, we've built a simple contacts database. Okay, and remember in the previous screencast we talked about a contacts, an ability in our RESTful architecture to send contact information back and forth. Well, I'm using the exact same contact representation here, but now we're going to make it persistent. So what you can see after we've run the jar task is we have this Berkeley DB-contactdb.jar file, and we can run that by doing java -jar Berkeley DB. And if we just do that without any arguments, it says, hey dude, you've got to supply some arguments. And this particular client does two things. It can put things into the database, and it can get things out of the database. In order to put things into the database, we have to supply the name, info, and unique ID field, and to get things out, we just ask for the unique ID. So let's start by supplying these arguments. So we'll say our first argument is Philip, our second argument is Johnson, our info field is Professor, and we'll use PMJ as our unique ID. So we run that, and oh shoots, nothing happens because I forgot the the command. Okay, I'll say this: the error checking in this client class is not the best. All right, so in the interests of pedagogy and code conciseness, I've not put as much error checking in here as I should. That sounds like an utter rationale, right, in the face of having a problem, but and it probably is. Anyway, that said, I'm going to add this put argument to the parameters, and what you can see here is the system comes back and says the context stored in the database, and then there's this line database closed, which I'll get to in a second, which tells you that that the database has been closed correctly at the termination of processing. So we run this system. Okay, now we want to see if it's persistent. Well, that particular program has closed. So if we now do, instead of a put, but now if we do a get PMJ, okay, let's see what happens. Okay, well, clearly things were persistent because actually when we call the get with the unique ID, we retrieved a contact and we've listed the correct fields. There's a couple other things we can do. Actually, it's not documented. We could call this delete command, and that will delete the that particular field contact from the database. And then if we do a get, we can see that we can't retrieve it anymore. Okay, so this is a client. It runs, it terminates execution, but we can see that we can put things persistently into a database and get them out later and delete them and so forth. Okay, where is this database, you might ask? Where this is stored is in a directory called contact DB in the directory at which the client is actually run. And I'll show you, you can put it anywhere you want, and I'll show you the code that ends up putting it in here. If we go in that directory, we see there's some files in there, and that stores the contents of the database. Okay, so that's the external view. Basically, all this system's quite simple. It's going to store and retrieve contacts from this persistent database. It's going to use Berkeley DB to do it. So now let's go take a look at the code and see how we actually built this system. So I'm going to go into Eclipse, and I need to import the project. Okay, so I invoke import. I'm going to import existing project into Workspace. I'm going to select the root directory. On my system, it turns out to be right here. And so I'm going to go open, and I get this particular project here. I want that one, so I'm going to click Finish, select Finish. And now I've got this Berkeley DB project in Eclipse. So the first thing I want to do is have you look at the build directory. And what you'll see is that we use Ivy to retrieve the Berkeley DB Java system. Okay, and Ivy is going to place the jar files for that system in the lib directory in Berkeley DB, and then of course we're going to include it in our class path, and we have a run ant command which will invoke this client class. Okay, and then I have a jar file which basically just creates a jar file that invokes that class as well. Okay, looking at the package level structure of the system, you can see that there's two primary packages. There's a client package, and then there's a contact DB database package where all the persistency stuff goes on. All right, so let's take a look. Let's start off by kind of exploring this database package in detail. And what you can see is that we have a contact class, okay, which is going to represent our information as a Java class. Okay, so you can see, and this is going to look almost identical to the contact class that we used in the previous screencast where we were talking about REST. We have a first name, last name info field. We have a unique ID. I've actually taken out the XML stuff from the previous screencast, so this is a little bit simpler. And then what you can see is that there are two special annotations, an entity annotation and a primary key annotation that were, and basically the entity annotation says this is a class which we want to have be able to be persisted using the Berkeley DB mechanism. Okay? And then whenever we have a persistent class, we need to specify in some ways what the primary key is for that class. And in this case, we're going to say this unique ID field is going to be the primary key. Okay? And in fact, if you can see, that's all we basically do to this class to make it persistent, which is super great. Okay? That's very low overhead compared with what you'd have to go through in order to store a class like this in a relational database mechanism like Derby or MySQL or whatever. Okay, so that's what we do to specify persistency within the class that we need to be persistent. Okay, then how do we store and retrieve these particular instances of a contact class? Well, what I did for that is created a class called Contact Data Access Object. Okay, and the structure of this class is a little non-traditional or different from what you're used to, and it's probably going to use a Java construct that you've never seen before, which is called a static initializer block. Okay, so this is a block of code which is run at the time that the class is loaded. Okay, and what this block of code does is it sets up two objects that are important for Berkeley DB to do what it's doing. Actually, it creates several objects. Let me go through them. The first thing it's going to do is it's going to create this environment config object, which is the way that so backing up a little bit, and I hope that you've done the readings first about Berkeley DB, but in Berkeley DB, to set up a Berkeley DB database, you've got to create something called an environment, you've got to create something called a store, okay, and then you've got to create something called a primary index, okay, which is kind of the handle you're going to use to get things into and out of the store, okay. So the environment object kind of basically says where is it that we're going to place the files. The store object is basically a way of specifying what kinds of objects or a partition of that environment where certain kinds of objects can be stored. And then the index is this mechanism that you actually can invoke methods on to get and put objects. Okay? So what we're going to do in this static initializer block, and the motivation for that I'll get to in a second. But the first thing we're going to do is we're going to say we want to store our database in a directory called ContactDB, which is a subdirectory of the directory that this program is being run from right now. Okay? And in order to do that, we've got to kind of build this path, which we do with these two lines of code right here. And then we call this makeDirs method of the file object, which creates these directories if they don't exist already, and we just, for kind of housekeeping purposes, print a line of output when we've created it and it didn't exist before. Then create one of these environment config Berkeley DB objects, a store config Berkeley DB objects, which are objects which allow you to configure the corresponding environment and store objects. And in both cases, the reason why we need these configuration objects is because we need to say if this environment and if this store does not already exist, it's legal to just create them. Okay, so we call those two methods. Then we create our environment object. We create our entity store object by passing an environment, giving it a name, passing its configuration parameters. And then we're going to store that entity store object in this particular static variable. Okay. Then we're going to create this primary index object from our store object, and for that we pass the type of the primary index, which in our case is a string, as well as the class that we're going to store in this store. Okay, and that's going to be called our contact index. Okay, now we're going to do something else, okay, which is kind of cool and is a little feature of Java, not well known but tremendously useful. They're called shutdown hooks, because one of the things that we need to do is with Berkeley DB is guarantee that whenever the system exits, we want to make sure we close our entity store and close our environment in order to just make sure that everything is cleaned up and everything looks good before we terminate execution. The problem is that one of the typical ways in our systems that we terminate execution is by typing Control-C, and then of course there's all sorts of exceptions that could be thrown or other reasons why execution could terminate abnormally. So Java provides a mechanism called shutdown hooks, which enables you to write code which is guaranteed to be run whenever the system exits for either normal or abnormal reasons. Okay? And this is super nice because it enables us to guarantee that we can close our environment and close our store every time the system exits, no matter how it's done. And that's pretty easy to do. We're going to create, the way we do this is we have a special class that we're naming database shutdown hook. It's an instance of the thread class. When we create an instance of it, we're going to pass it the environment and store that we're interested in, and we'll store those. And then we have a run method, which is going to be invoked by the system whenever the system is about to exit. And what it will do is check to see if the environment is not null, and if not, that means that the close method should be called. And if there's an exception raised, which shouldn't really happen in practice, we will print out a message to that effect. Okay? So we have to create this kind of shutdown hook thread class, and then in order to get it to, we create it right here in this line here, and then in order to make sure that this thing gets run when the system exit, we use this special magic, runtime.getRuntime.addShutDownHook, and then we pass in this instance of our class, which is actually just an instance of the thread class. Okay, and that run method will be called. Okay, so that's pretty cool. Okay, so that's the code that's inside our static initializer block. And now the question is, why do we have a static initializer block? What's the purpose of this? And the purpose of this is that we don't in Berkeley DB want to have multiple environment instances and multiple entity store instances running around our system at the same time, all pointing to the same place, okay, the same files on disk, because that can lead to problems. So how can we do that? Well, we could create a singleton object. There's a variety of ways to do it, but a particularly nice way to do it in this particular situation is to use a static initializer block, which is code that will be run one and only one time whenever the class is loaded. Okay, so when this class is actually loaded, we'll get this code being run, and that means that, and then we can initialize these static fields, right? And a static field in Java is one where that means it's associated with the class definition, not an instance definition. So all instances share, these same fields. They don't have separate ones. So the net of it is that when we run this static initializer block at class loading time, we are going to define and set the values of these variables. Okay, which means we'll only have one store instance of an entity store, and we'll have only one instance of a primary index. Okay, that's the whole purpose of doing this via static initializer class. It guarantees we can't have two of these things. Okay. Now what we also have, once we've done that, we can simply have, again, these static methods where you pass in a contact and we call the put method of our primary index object to store it in memory. We call the get method of our primary index object to retrieve it from the persistency manager and return it. And then finally we have a delete one, which does delete. Okay. Now what's cool about this is that this contact instance method is completely thread safe. Okay. So if you remember in our previous screencast when we had that contact database, or the contact, I forget what it was called, but I think it was the contact class, we had to synchronize, it might have been contact, or the contacts, that's what it was, the collection class contacts. Remember how we had to synchronize access to that class to make sure that the class was thread safe. Here you don't see any synchronization. We can have as many threads as we want accessing these primary indexes as frequently as we want without any problems of thread safety. Okay, so this actually turns out to be a very high performance implementation of a persistency manager with very little contention that can result from having to do synchronization and so forth. Okay, so that's the contact data access object class. Okay, and really the only, well, the second to last class that I'd like you to look at is this test class, which kind of shows how it is that we can see that our contact data access object works. So in this test contact database method, we're going to create unique IDs for two contacts. Then we create these two contacts, one that kind of represents me and one that represents my colleague down the hall, Dan Southers. And then we basically just take the contact data access class, we call the static method put contact with one, and then we call it with another one, and now those two contacts are persisted in the database. Okay, we can then retrieve those contacts, okay, by calling the get contact, and now we've got a second instance of that contact, right? So contact 1 and contact 1A are two separate instances of the contact class, but they have exactly the same contents. Okay? Similarly, contact 2A and contact 2 are two separate instances of the contact class with the same thing. And then to check that that's actually true, because that's what we want to have be true, what we do is we call their two-string methods and check to make sure that they're equal. Then finally we call delete contact, given one of our unique IDs, and the get contact method will return null when the object is not found, and so we just assert that that's null. Okay, so just to prove that this works, we'll invoke JUnit, and we get the green bar. So all of this is working as expected. Okay, the next thing I want to do finally is show you our client class, okay, which is the one that we invoked from the command line. Okay, and so the first thing we do is we check to make sure that there are some args provided, and then we do this usage showing the put and get commands. And then if we have at least two arguments, then we check and see what the command is. If it's equal to put, then what we do is we read the remaining arguments and we construct a Java contact object from it, and then we invoke the put contact method to put that contact into the database. And then we just print out the fact that we've stored that. If the command is get, then we get the first, well, actually the second argument, which is the unique ID of the contact that we want to retrieve. We call the get contact method of our contact data access object class, and that will either return null or the actual contact instance that we're interested in. And then depending on whether it's null or not, we print out information about it. And then finally delete. We get the unique ID again, and we call delete on it. Okay, so that's the way this works. And I challenge you to find a persistency mechanism which is simpler, significantly simpler, than just annotating our class with the fact that it should be persistent and what its primary key is, and then writing about, essentially 15 lines of code to set up the database, and then, one-liner methods to do retrieval and getting. Okay? So now, all right. Obviously, those of you with some database experience will say, listen, dude, persistence is a lot more complicated than just storing and retrieving individual objects. There's joins, there's much more complicated queries. You're not showing me any of that stuff. What I will say in response is that Berkeley DB actually provides some nice facilities. It provides secondary keys. It can allow you to retrieve ranges and do all sorts of more complicated things, but you'll have to read the documentation to see how to do it. What I will say is that the implementation of those mechanisms is basically, order one as complicated as these particular implementations as well. So it enables you to do most kinds of things that you'd want to do in an object database in a very convenient way. It has built-in in-memory caching, so that the performance can be really good when you're repeatedly accessing the same kind of object. And there's things that you do give up. It's not a perfect persistency manager by any case, but as I hope to kind of say in the initial part of this lecture, every single persistency mechanism comes with trade-offs. And it's the best one for your needs really depends upon the specific context that you're working in. But I think you'll find that working with Berkeley DB is an enjoyable experience and is a nice option to have in your toolkit for certain kinds of circumstances. So take a look at this, download it, run it, do the katas to get more familiar with some of the more advanced features, and I'll see you soon.